Hello, my name is Ahmed and this is a new DevOps video. Today we are going to learn how we can deploy a Kubernetes cluster on AWS using Kubeadm. There are many ways you can deploy Kubernetes on the Amazon platform, including KUBS, Kubespray, AWS EKS, which is a cloud managed offering, and Kubeadm. So, why would you think of using Kubeadm and not one of the other methods? Well, simply because Kubeadm gives you the maximum amount of control over every bit and piece of the cluster installation process. While not intended for production setups, this method provides a great learning experience. So, without any further ado, let's get started. In this lab, we are going to use Terraform as our infrastructure as code tool. It will create the required infrastructure components. Let's start by exploring those infrastructure components first. A Kubernetes cluster on AWS requires at least one private subnet for hosting the master and worker nodes, at least one public subnet for hosting the jump server, which would be used to SSH into the protected nodes, and also for the load balancer to work. When I say at least, this is because ideally you will need one subnet in each availability zone of the AWS region of your choice to ensure high availability. Also, we need IAM roles that enable master and worker nodes to talk to the AWS API server and do stuff like launching load balancers or gaining information about other components. We also need security groups to be attached to master and worker nodes to control network traffic security. Now let's get our hands dirty. Start by creating a directory called Terraform. Inside it, run Terraform init. In this lab, I assume that you have Terraform installed. If not, you can go ahead and install it from this URL. Create a file called main.tf. This is our Bootstrap file and it will be used to call any modules that we define later on. The contents of this file should be as follows. The provider is AWS and the region is EU West 1. You can choose another region if you want to. Then we configure Terraform to use an S3 bucket to store its state. This is highly recommended so that you don't lose your infrastructure state simply because you are running Terraform from a different machine. This bucket should be manually created first. Terraform will not create that for you. Then we call a module called Kubernetes and inform Terraform that this module can be found in a directory called Kubernetes. Let's create a subdirectory called Kubernetes that would hold our module files. We are going to place all our Kubernetes code in a module so that we can reuse it again as needed. We'll start by creating the VPC. Create a new file called vpc.tf. This file will be responsible for creating and configuring our VPC. We'll use Terraform's AWS VPC resource and we'll call it main. Our VPC will need a CIDR block. As a best practice, we tend to use variables whenever possible to make our module reusable. So, instead of hard coding our CIDR block, we use a variable. However, Terraform needs to know that you intend to use a variable called VPC CIDR block. So let's create another file called variables.tf and add a variable definition. We need to specify the variable name and its type. Maybe asking when we are going to supply a value for this variable. Well, we'll do that when we call this module later on. For now, just make sure that you use variables and not hard-coded values. Now let's get back to our VPC. Since Kubernetes uses certificates for securing communication between the nodes and the API server, it needs to be able to call the nodes by their DNS names rather than IP addresses. So we need to enable DNS host names and also instruct the VPC to use AWS's internal DNS server. Finally, we need to give this VPC a name to be easily recognized. So we define a tag with a key of name and a value that can be chosen by the user later on. Let's not forget to add a variable with the same name in the variables file with a type of string. Next, we need to ensure that the internal DHCP server that the VPC uses assigns the correct DNS names to the EC2 instances. So we use the AWS VPC DHCP options and configure the domain name to be region.compute.internal. So, for example, if we are operating in the EU West 1 region, then all our instances will be assigned a DNS name that ends in EU West 1.compute.internal. In the same Kubernetes directory, create a file called networking.tf. This file will be responsible for deploying and configuring our subnets and route tables. We'll start by creating the subnets. We use the AWS Subnet resource and call it private 01. The AWS Subnet resource requires the VPC ID, so let's get it from our VPC resource output. We don't want to assign a public IP to the instances that get created in the subnet, so we set map public IP on launch to false. Each subnet needs a CIDR block that is a subset of the main CIDR block that we chose for the VPC. For example, if our CIDR block is 10.240.0.0/16, then a possible subset would be 10.240.1.0/24, 10.240.2.0/24, and so on. In this lab, I will use the first 8 bits of the CIDR range for the host. Terraform provides a built-in function called CIDR subnet that would automatically calculate the subnet range for you based on some input. So we'll use it as follows. CIDR subnet, then we pass in the CIDR block of the VPC, the number of bits that I want to use for the host, and the network ID number for this subnet. You could hard code the network ID here, but if you want to create more than one Kubernetes cluster in the same VPC, you will need to select a different network ID for each subnet you create. So let's use a variable for that and make it up to the user to select an unused subnet ID when calling the module. Next, we need to select an availability zone for this subnet. Terraform provides a data source that will automatically enumerate all the availability zones for the region that Terraform is using. Let's call that data source before we start creating our subnets. This data source returns the availability zones in a list, so we use Terraform's element function, which allows us to select an item in a list based on its index. We pass in the availability zones and select the first one, index 0. Now we need to define the subnet tags. Let's add a name to the subnet. It could be anything you want, but I recommend that you use a naming scheme for easier administration. In this lab, I will use private-subnet, then a sequential number followed by the name of the cluster. Next, we need to define a mandatory tag, kubernetes.io/cluster, your cluster name, and the value of this key is shared. Without this tag, Kubernetes is not able to recognize this subnet as its own. You can also optionally define a tag that allows Kubernetes to create internal load balancers by using this subnet, kubernetes.io/role/internal-elb, and set it to 1. To create the public subnet, we can just very easily copy and paste the private subnet code in here and make a few changes. The CIDR block needs to use a different network ID, so we define a new variable for the public subnet netnum. We need to assign a public IP address to instances hosted in the subnet since it is public. We need to change the load balancer tag from internal-elb to ELB so as to allow Kubernetes to create public-facing load balancers in this subnet. Let's also create a utility subnet. A utility subnet will be used to host the NAT Gateway, but it can also be used to host other components that do not strictly belong to Kubernetes, like the Bastion server. Again, we can copy the code from the public subnet resource and remove the unnecessary parts. Let's create public and private routes. The only difference between them is that the public route contains an entry to the Internet Gateway, while the private route doesn't. So let's use the AWS route table resource and create private RT and public RT. They only need the VPC ID as a parameter. To deploy the Internet Gateway, we use the AWS Internet Gateway resource, which again only needs the VPC ID as a parameter. The NAT Gateway is slightly more complex. It needs a subnet and a static IP address. We've already created the utility subnet to be used by the NAT Gateway, so let's create the elastic IP. We use the AWS EIP to deploy an elastic IP resource. We set the VPC parameter to true. Now we can deploy the NAT Gateway by using AWS NAT Gateway resource. We pass the elastic IP ID as an allocation ID and the utility subnet ID as the subnet ID. We get to select which of our routes are public and which are private by attaching the Internet Gateway and NAT Gateway respectively. We start by creating a route to the Internet Gateway using the AWS route resource. We instruct this route to be attached to the route table called public 01 and route all traffic to 0.0.0.0/0, which is everything that is not intended to the internal VPC, to the Internet Gateway. Our second route is called NAT Gateway. Again, we attach it to the private route table and instruct it to route any traffic to 0.0.0.0/0 to the NAT Gateway. We need just one extra step here, which instructs Terraform not to start configuring this route unless the NAT Gateway is up and running. The reason is that the NAT Gateway takes a considerably longer time to deploy, and we need to ensure that it is there when the route is created. Otherwise, the procedure may fail. Now that we have our route tables configured, we need to link them to our subnets. This is done using the Terraform's AWS Route Table Association resource. Since we have 3 subnets, public, private, and utility, we have 3 route table associations. We need to create a number of security groups and security group rules for our EC2 instances as well as the load balancer that we are yet to deploy. Create a new file called securitygroups.tf. We start by creating a security group for the API load balancer. As mentioned before, this load balancer is responsible for routing traffic to the Kubernetes API server in case you have more than one master node. We use the AWS security group resource, give it a name, associate it with the VPC, optionally add a description. Then start defining our rules. We need this load balancer to accept traffic on port 6443, which is the port that we will be using for the API server. Optionally, we define another rule to allow ICMP traffic such as ping to reach the load balancer. Then we define our egress rule to allow outgoing traffic from the load balancer to anywhere. Finally, we define a couple of tags for that load balancer to be recognized. Whenever we need to SSH into one of our worker or master nodes, we need to use a bastion or jump server to tunnel the connection. This bastion server is in a public subnet and must expose port 22 for SSH access. Let's create the necessary security group for that. Now we need to create a security group for our worker nodes. The rules we define should ensure that worker nodes can receive traffic from any node on the same VPC. So we define our ingress rules to accept all traffic from the VPC side block. And as usual, egress is configured to send to any target. Here we need to add the required tags so that Kubernetes recognizes and uses this security group. The master node security group is slightly more complex, since we need additional security for the master nodes. The security group needs to ensure the following. Traffic from the load balancer to the API server on port 6443 is allowed. Traffic from the worker nodes is allowed. SSH traffic from the bastion server is allowed, and no more. So, to make this happen, we need to define our security group rules separately and attach them to the security group. The reason is that Terraform needs a separate security group rule resource when we need to allow traffic from another security group. Let's start by defining the security group. Notice that it does not contain any rules, only the name, description, VPC ID, and tags. Next, we define our first rule, which is to allow traffic from the load balancer to the master nodes. The AWS security group rule requires a type, optionally a description, the source and destination ports, the security group ID that this rule will be attached to, then the source security group. Any components that use the source security group are allowed to send traffic to this security group on port 6443. So, we use the security group ID of the load balancer. We can reuse this technique to add other rules as required. All traffic from worker node security groups, SSH traffic from the bastion server's security group. Finally, we define the egress rule in the same fashion. Before attempting to create and use the EC2 instances, we need to create the necessary IAM roles and permissions. Those roles are used by the master and worker nodes to connect to the AWS API to perform actions like spawning load balancers, for example. Create a new file in the Kubernetes directory and call it iam.tf. We start by defining an AWS IAM policy document that will serve as a trust document. The purpose of the trust document is to enable EC2 instances to assume IAM roles by creating a trust relationship between IAM and the EC2 service. Next, we create the master IAM role, which would be used by the master EC2 instances. We define the role name and the trust policy. Now let's create an AWS IAM policy that would define the permissions that this role should use. The permissions in this file are loosely taken from the KUPS repository. Please make sure you carefully review them and only use the needed ones. We create a similar one for the worker instances. Finally, we create the instance profiles for the master and worker instances. An instance profile can be later attached to an EC2 instance to allow it to use the role defined in that instance profile. Now we define the EC2 instances for the worker and master nodes. Create a file called nodes.tf. We start by creating an SSH key pair that would enable us to log into the instances. On your shell, issue the following command: ssh keygen -m pem -f ssh key. The -m specifies the key format. We need a pem key, while the -f switch specifies the name and path of the key pair file. Now we need to copy the public key. In our nodes.tf file, we define an AWS key pair resource and pass in the public key data. Finally, we give that key a name, SSH key, for example. This will ensure that our instances are accessible by our private key. We need to use an AMI for our Bastion server. You can use any Linux or even Windows-based machines. In this lab, I will use the latest version of Ubuntu 20.04 AMI. Terraform already provides a data source that grabs the AMI ID. Defining the Bastion server is pretty easy. We just need an EC2 instance that uses the Ubuntu 20.04 AMI. So we use the AWS instance resource and pass in the AMI by querying our data source. The instance type, the security group, the key pair that we've just defined, subnet ID. We'll place the Bastion server in the utility subnet. Dedicate a 20 GB disk for the root volume and optionally add a tag. The load balancer is needed so that we can have more than one master node. We use Terraform's AWS ELB, give it a descriptive name, then we define a listener. The listener accepts connections on port 6443 and forwards them to the backend instance on the same port. Next, we need to define the security group. We use the security group that we created in an earlier step. In the subnets part, we only have one public subnet, so let's use it. The load balancer needs a health check to make sure that the backend nodes are healthy, so we define it. Optionally, we enable cross-load balancing since it's disabled by default, and we define an idle timeout of 5 minutes. Don't forget the required tags. For the master and worker nodes, we use autoscaling groups. They ensure that we can dynamically increase or decrease the number of nodes. They also guarantee that a node will be replaced if it got terminated. An autoscaling group needs to launch a configuration that defines how each node is spawned. Let's define the launch configuration for the master nodes. We use the AWS launch configuration. We pass in the name prefix, which will precede each node name in the group, the image ID, which is the AMI that we use for this autoscaling group, we need to supply it as a variable. The instance type defines the instance type and size. This too needs to be a variable. The key name is the SSH key pair defined earlier. The IAM instance profile needs the ID of the instance profile that we created in a previous step. Security groups refer to the security groups that should be attached to the instances hosted in this autoscaling group. The user data defines a script that should be executed once the instance boots for the first time. In this user data, we need to change the host name to match the DNS name of the instance. We can get the DNS name of the machine by using a special API provided by AWS. On any EC2 instance, if you run curl 169.254.169.254/latest/metadata/localhostname, you get the DNS name of that instance. So we can set the host name using the hostname CDL. The root block device is the disk that will be used in the instance. We select the disk type, size, and instruct the instance to delete this disk when it gets terminated. Now we can create the autoscaling group using the launch configuration. We supply the name, the launch configuration, the maximum number of nodes. We are using only one master node for the setup. The minimum number of nodes is also 1. The subnets that this autoscaling group will use, we only have one subnet. And for the master's autoscaling group, we need to attach the load balancer that we created earlier. Then we define the required tags that each instance in this autoscaling group will have. Notice that we use the propagate at launch property to ensure that the tags get attached to the instances at launch time. For the worker nodes autoscaling group, we replicate the exact same code with some minor differences. So we change the name, the instance type, and the IAM profile. Finally, we add the appropriate tags. Now that we have our Terraform manifests done, let's start by heading to the terminal and running Terraform init, followed by Terraform plan and Terraform apply. In a few minutes, we have our infrastructure deployed successfully. Let's have a look at the AWS console and view the instances that were created for us. Let's grab the IP address of the bastion server. Now on the console, let's ensure that our private key has the correct permissions. Then let's log into the master node using the jump server by using the following SSH command. We need to grab the private IP address of the master server. Once we are in, let's create a kubeadm.config file. We need to define a cluster name. Let's name it Sky Valley. We also need to define the API load balancer's URL. Now let's save the file and run the kubeadm init command, passing in the kubeadm.config file as a parameter. I'll fast forward the video at this point. Once the cluster is bootstrapped, Kubeadm prints the necessary command to join a new master or worker nodes. Let's copy the appropriate command and head on to the worker node. Let's grab its IP address and paste the Kubeadm command there, preceded by sudo since it needs root privileges to run. Now let's move back to the master node and install a network CNI plugin for the cluster to work properly. In this lab, we'll use WeaveNet. To ensure that our cluster is running properly, let's list the nodes by issuing kubectl get nodes. Notice that we are using the kubeconfig file located in /etc/kubernetes/admin.conf. Using that same file, let's grab the paths in the kube system namespace. This concludes this lab. In this video, we use Terraform to deploy the required infrastructure for deploying a self-managed Kubernetes cluster. If you've got any questions, please drop me a comment, and if you like this video, please remember to press the like button. Don't forget to subscribe to my channel to get notified about new content. Thanks for watching, and see you in the next one.